What we're talking about here is something called the standard cell. And we are discussing how this basic experiment was used to identify how well redox reactions occur, and sometimes how they don't occur. It explains why some reactions occur very well and some do not occur at all. And it centers around voltage. Okay, this idea of voltage is something we call potential difference. Now, the reasoning that I'm talking about the standard cell and using voltages, okay, is because, and I'll just put potential difference here, potential difference in charge. And the reason I'm discussing voltages is because the size of this potential difference in charge, now the charge I'm talking about is a difference in positive to negative. Okay, so if we're talking about a high voltage, there's a great difference between the positive and negative. Okay, and that creates a flow of charge through a circuit. But again, as I keep starting and stopping, the voltage, okay, is something that we use to really measure something called spontaneity. Now, whether a reaction occurs, whether it's a redox reaction or any reaction in thermodynamics, we say if a reaction occurs under a set of conditions, it is spontaneous. The neat thing about electrochemistry, if we can look at the spontaneity or how well a reaction works by really the difference in charge between something that is oxidizing and something that is reducing. Think, if electrons are being passed around from the object that is oxidizing to the one that is reducing, okay, we can get a current, and that's how batteries are essentially formed. Now, we're not talking about current and voltage here. Current is amperage, and amperage is coulombs or charge over time, okay? But what we're talking in voltage is the potential difference in charge. Why is there an ability for electrons to flow from the object that oxidizes to the one that reduces and gains electrons? The reasoning is in the ability of the chemicals that can give off electrons and accept. Okay, what I mean here is that if I have a chemical or a chemical agent here or species that's good at oxidizing, it can push its electrons, okay, through a circuit. And something that's good at reducing can pull charge or electrons through a circuit. And when you do so, you create a potential difference. Okay, sometimes they call this voltage an electromotor force. Okay, and you'll see this as E of cell. Okay, now you'll see E of cell little zero, and that's because under standard conditions, okay, 1 molar concentrations or 1 atmosphere of pressure, okay, we measure the actual voltage between objects that love to oxidize or objects that oxidize with objects that reduce. And we can measure this combination of pushing and pulling through a circuit, okay, by the voltage. Now, voltage isn't current, it's a potential for current. So if I have something that's great at oxidizing and something that's great at reducing, there's a large potential for current to flow. That doesn't mean that electrons are flowing at a high rate and therefore give us a tremendous amperage. It just means that it creates a pathway, okay, or a direction for electrons to flow. Otherwise, spontaneous. We talked about delta S, okay, entropy measures, or delta G, we talked about, okay, measures direction. Okay, we're not going to get into that here, but that's what we're after. Now, of course, other factors that affect the amperage are surface area and other things here, but we're just talking about the potential difference. Where is there a great potential and direction for charge to flow because of this pushing by the object that oxidizes and to the one that pulls by the reduction? Okay, and that's where we get a measured voltage. Okay, now, for those that are still having some trouble with this voltage, think of a waterfall. Okay, a waterfall, okay, water flows from a high place to a low place, obviously. Now, a waterfall, okay, you can use this analogy in voltage. Voltage represents basically the height of the waterfall. Okay, so the higher the waterfall, the great potential for the force on the bottom to be high. Okay, any case, if you have only a small amount of water dripping through your waterfall, then your amperage, okay, is going to be low. The actual current, the flow of water, just like the flow of electrons, is actually going to be low, okay? But its potential is still high, all right? Now, if you were to somehow increase the amount of electrons that can flow in this pathway, well, as the electrons or as the water increases in volume, okay, wow, the amperage it will be incredibly high if the voltage is high. So voltage is the potential really for the amperage to flow. If the voltage is low, that would mean that you have a terrible pathway for electrons to flow. There isn't a great difference in charge being created by these two different parts of a redox reaction, and only a little bit of electrons can flow no matter how you make the electrons available. Okay? So just because you have a high voltage doesn't necessarily mean you have a great number of electrons. It's dependent upon, okay, what electrons are available in your system to flow. But a high voltage provides a pathway for a high potential for electrons to flow. A low voltage, okay, no matter what you do with your electrons in your system, can't really produce a high amperage because there isn't a great pathway. All right, so again, voltage and amperage. Voltage is a pathway, amperage is the amount of moles of charge being passed around. So they have a saying that voltage will throw you. It's a force, okay, at least in that analogy, but amperage will kill you because of the charge, okay? And it kind of explains some of the abilities and some of the tragic accidents happening in electricity. Any case, moving forward, all right, what do I have here, okay, is something called a standard cell. Okay, and this standard cell, I'm trying to measure the potential difference between individual objects that oxidize and individual objects that reduce. So I'm trying to find some kind of standard to use to put some volts down for individual reactions. There's a reason for this, and I'm going to get to, okay, hopefully. All right, so what am I going to do here as I get rid of some of my stuff here out of the way? All right, so what I'm using is hydrogen. We found that hydrogen, okay, seems to be in the middle part of a lot of our reactions, and it's an easy one to standardize. So what we have is hydrogen gas, okay, at 1 atmosphere of pressure. And that's pumped in to this little tube here. Then I have 1 molar solution of H pluses, also in the same area. So I have an H plus solution here. Okay, I have H2 gas in here, both at 1 molar, well, this is 1 molar, this is 1 atmosphere, but we call these standard conditions. Okay, now in my drawing here, I have magnesium here, but what we do is you put a lot of different elements. But let's start with reactive metals. We know that magnesium, we know that calcium, we know that barium, these are group 2 elements, and group 1, okay, are very reactive. Why they're very reactive? Because they're so big. Their electrons are so very far away from their nucleus. They're able to lose their nucleus very easily. They oxidize very easily. So when I put different elements that oxidize very easily, what they normally do is they push their electrons. So if I oxidize really well, which by the way, Leo the lion says, losing electrons is oxidation. So if I lose electrons, I'm oxidation. So electrons are lost, but really they're kind of pushed. And I know that we're not talking about electrons traveling, but I'm using the analogy of forcing its electrons through this external wire. So it's able to, you know, push its electrons and create a potential here. Now, the question is, I have H2 available at this electrode. Now, the platinum wire is my electrode. It's a place where oxidation and reduction can occur. It itself is really resists oxidation reduction. So it's just basically a conductor. Okay, so I have hydrogen and H plus. Now there's two reactions, or two possible things that could happen. I can take hydrogen, okay, and it could basically lose an electron, or in this case lose two electrons, and become H plus. We would call this, of course, oxidation. That is one thing that can be done. All right. And then second thing that could happen was pretty much the opposite. The H plus that's in the solution already could gain two electrons and make hydrogen. And of course that's a reduction because our charge is going down, getting reduced because we're accepting electrons. So there are certainly two things that could happen here. The question is, which one occurs? All right, well, we have a voltmeter that's measuring the potential difference. And, well, if this element is so good at oxidizing, it will force the electrons to flow, or I'm sorry, it'll force a potential difference in charge, okay, to be great here, and it'll cause, okay, these electrons that are producing a potential difference will cause the H plus to get reduced. Okay, so think of the, and this is an analogy, but think of the magnesium forcing its electrons on this current, on this conductor, and think of the H plus pulling these electrons forward. So I've got the magnesium pushing the charge this way and the H plus pulling on it to create a potential, a pathway for charge to flow. And we would get, okay, positive volts in the voltmeter. Okay, this would be a spontaneous process. Now the reasoning is this, okay, magnesium is a strong enough element at oxidizing, or I should really say that magnesium is a strong enough reducing agent that forces the electrons onto the H plus to cause there to be positive volts. Positive volts means it happens. So very reactive metals, okay, that can lose their electrons easily can force the reduction on a lot of different compounds, and we get positive volts, okay, in this scenario. Okay, now you can look at it a couple different ways and say, well, if I set it up the other way, if I change my points of contact here, my voltmeter, you could say it gives negative volts, but we're going to say this is spontaneously occurring this way and make it stay positive. Okay, so we get a positive voltage. Now what we're going to say is we're going to say that the amount of voltage we get is primarily due to the ability of the magnesium. We're going to make hydrogen the standard. So we're going to say theoretically it has 0 voltage to make it happen. It's not really true, okay, but we're going to say it's the standard. So we're going to compare many different elements in this position and we're going to see what it does. All right, so strong elements like magnesium, okay, or very reactive lithium, okay, all group 1 and group 2 will force, in this scenario, positive volts to occur. And the funny thing is, well, not that funny, if I have a more reactive element than magnesium, it would force a higher voltage along the way. Now, so we can start measuring this voltage, all right, and we start writing down the actual voltage. So if I was to hook up now sodium, okay, now sodium has a different ability to lose electrons, so it has a different push on this circuit or this charge or this potential difference. It will create different voltages. Okay, so I'm going to pause and I'm going to show you these on something called a net potential table. Hold on. And here is something called a standard reduction potential chart. And maybe a little different from what you see if you're not in my class. I'm using the one that's showing negative voltage for the reduction here. Okay. Sometimes I'm seeing negative voltage for the metals, okay, um, because I'm showing, I should really say that I have the metals up top, whereas other charts have the non-metals up, like fluorine on top. So let me show you something here. And the reason why I'm using this table is because something in New York State, we have a table J that's built from this actual representation, but the charts are very similar and the same in their construction. Now, if you notice something, here's the standard cell. 2H plus is gaining 2 electrons to make hydrogen gas is 0, and if you go in the reverse, it's 0. Now, that is what we have here. That's our standard cell. That's what we use to get all the other voltages. Now, if I want to take elements and I want to figure out their individual ability to create a potential difference, okay, a voltage for their half reaction, I connect it up to my standard cell, and I compare it to the standard cell. For instance, in the example that I just drew for you, okay, we had magnesium. Let's go find magnesium, okay, and here's our magnesium, and magnesium was oxidizing into Mg plus 2 to give off 2 electrons. It's the opposite as it's written. And if you notice, this is a reduction table. So they write it in the form of reduction. Now, we would actually get positive 2.37 voltages going this way. So magnesium loves to oxidize. So we get positive 2.37 voltage. Now you may say, Mr. Grodsky, why is it written negative? Well, because they list these potentials in their reduction form. So in the drawing I just gave you, and let's go back to it, all right, I've got magnesium, okay, hooked up with the H pluses. There's reduction by the H2, and there's what? There's magnesium, okay, giving off its electrons to the H plus through this circuit, creating a potential difference. So there's a positive voltage because this will work, but this magnesium is oxidizing. So if we write it as a reduction potential, it goes negative, but we know better. So if I was to give you calcium in that same system, calcium actually loses electrons better than magnesium, and when it oxidizes going this way, it gives off a better positive. So you can see that this is a list of reactive metals. Okay, if I was to give you metals that weren't very reactive, let's go all the way down. Look at gold. Gold is going to oxidize. What would be its voltage? Negative 0.5 volts, which means it does not work. Negative voltage means that's the energy you have to add to make it happen. Gold resists oxidation. Okay? Now, how do we measure this value? Well, if I have gold in this system, okay, in the system that I have, let me show you. We put gold here, all right, so forget the magnesium, let's make this gold, Au, and I put Au plus 3 in here. 1 molar solution, this is a gold, assuming no one takes it. Well, gold is terrible at oxidizing. Hold on to your ponies now. Things change. Okay, now gold is terrible at oxidizing. Au plus 3 is very good at reducing. So what happens here is this Au plus 3 pulls, okay, electrons, right? Au plus 3 gains 3 electrons to make pure gold here, and it pulls electrons this way. Now, if it's pulling electrons, it's forcing something to what? Oxidize. The hydrogen gas that was sitting in here now can oxidize. Okay, and we get voltage flowing this way. And it'd be a negative because we're going the opposite the way it was, but it doesn't matter. We can measure that voltage. Okay, so we'd measure how well this happens. So Au plus 3 is a strong enough reducing agent to make, oxidizing agent to make the hydrogen oxidize, whereas the gold was too weak of a reducing agent to form the H plus go. So we can measure that. So we go to our table, all right, and we see that gold didn't work under that set of conditions, but the Au plus 3, okay, can what? Can force okay, the what? Hydrogen to oxidize. And we would measure that voltage of reduction to be, okay, 1.5 volts. Now, in truth, my system, the way that I had it set up, would be negative 1.5 volts. But we know that gold is happening, and we write everything as reduction. And what we have here is a reduction chart that shows us how well things reduce, right? Because these voltages are increasing for the what? For these guys reducing, or the oxidizing agents. Look very carefully. Fluorine's the best at getting reduced in this scenario. Okay? So therefore it has the largest reduction potential. And that makes a lot of sense. Fluorine loves to pull electrons from things. Look at oxygen. We got the word oxidation from what oxygen does to do this. But look at fluorine. Fluorine has the ability to yank electrons from all of these compounds. Okay, so quickly as I finish this standard cell explanation, this H2, okay, and H plus system that are available as either the gas or in solution make the reaction spontaneous one way or the other. Okay, so we either force the what? Oxidation of hydrogen by a strong oxidizing agent, okay, or in this case, and I'm sorry, and we force the reduction, okay, like in the case of when you had the magnesium in group 1 metals, we forced the reduction because these are strong reducing agents. And of course, to make the hydrogen become H+, we have a strong reducing agent. So basically, we set this problem up so that either this half reaction or this half reaction is forced to go by the action of either the metals in the electron or the ions in solution. And that's how we came up with the voltages that can tell us something about the spontaneity of the entire reaction. So that's why it's the standard cell. Now we can look at this and say the most reactive metals are here. They love to oxidize, which means their voltages are going to be very positive when they go in the reverse, but their ions hate to reduce, okay? So that's why they're negative. So these are the worst at reducing, the best at oxidizing. These are the best reducing agent. These metals can force the reducing of other elements. They can force all of these to reduce. Whereas these elements are so good at what? Reducing, they can force all of what? All these elements. All of these guys can force all of these elements above them to oxidize. And that'll give you positive volts overall.